Okay, clear to go.
Great. Thank you. Hello, Seattle. This is Utrecht calling. And thanks for the organizers for putting together a great program and inviting me to talk about my JFP paper. So the title of my paper is A Well-Known Representation of Monoids and its Application to the Function Vector Reverse. And I'll explain where that title comes from in a little bit. But actually, the paper is much more about finding the right definition, just as Connell mentioned in his talk. So what do I mean by that? Well, according to the Oxford University Dictionary, a definition is a precise statement of the essential nature of a thing, a statement or form of words by which anything is defined. But for the purpose of this talk, I'll mostly focus on definitions in AGDA. So in AGDA, you can declare data types, like the natural numbers, closed under 0 and successor, and you can define functions like addition. So here I've defined addition by induction on the first argument. And of course, given that this is a talk about AGDA, it should really also mention vectors. So you can also define vectors, which are length indexed lists, where you keep track of the length of the vector statically in the type. So the empty vector nil has length 0, and the cons a non-empty vector takes a head and a tail and builds a vector which is one longer. And then the next thing we can do is we can define an append function which takes one vector and appends it onto the next. But this is actually quite subtle, and it's quite surprising that it type checks at all. And because I'm going to do some more crazy stuff in the rest of the talk, I figured I'd take the time to kind of explain what's going on here very precisely. So if we look at the first clause for append, what we're promising here is to produce a list, or a vector rather, of length n plus m. But because we've pattern matched on nil here, we know that n is 0. So the goal that we need to prove, or that we have to deliver on, is providing a vector of length 0 plus m. Now what I'd like to write on the right-hand side is just to return y's, and that is a vector of length m. So by definition of addition, I know that 0 plus m is equal to m, and this will actually type check. So I've marked it in green here. So what about the cons case? Well, in that case, I kind of promised that I would return a vector which has length successor of k plus m. So because there's a cons, I know that n needs to be a successor of some number k. And if I kind of write out the usual definition for append, namely cons x append x x's, I can see that the cons x gives me a successor out at the front, and then the append of the tail and y's produces a vector of length k plus m. And now by definition of addition, once again, for the successor case, I can see that these two numbers are equal, and I'm done. So what's nice about this example is that the inductive structure of addition and append lines up precisely. So that's great because I kind of don't need to do any other work. But the bad news is that the only equalities you ever get for free are those that hold definitionally. So in particular, suppose I try to write a function on vectors where I kind of manipulate these numbers, I rely on addition being commutative. That doesn't hold definitionally, even if it's true. So I'd have to do some more work in order to kind of convince AGDA that that definition really does type check. And in a lot of talks on dependent types and vectors, people kind of show kind of append, and then they might do map, or they might do kind of lookup-like functions, and kind of the things which work out well. But the purpose of this talk is to kind of scratch the surface on things which are not so easy to define, but still possible. So let's look at reverse. First thing I can do in order to define reverse is define a SNOC operation, which kind of has the same type signature as cons. Only I've reversed the argument and I'm now adding things to the end of the list instead of to the front. And now you can see I can define a reverse function fine, which takes a vector of length n and produces a vector of the same length. So the empty vector is mapped to the empty vector, and if I have a cons, I replace it by a SNOC and recurse over the tail x's. And this is fine. Kind of AGDA accepts this definition. It's easy to see that reverse is a kind of length-preserving operation. But taking quadratic time to reverse a list is pretty bad, right? And even though we're kind of in dependent types land, you'd like to kind of show that that we at least can find a linear time algorithm to reverse a list. It doesn't seem like such a big ask. And we're in luck because there's a nice paper which inspired the title of my paper by John Hughes called A Novel Representation of Lists and Its Application to the Function Reverse. And this is the first sentence from the abstract, which says that a representation of lists as first-class functions is proposed, and lists represented in this way can be appended together in constant time and can be converted back into ordinary lists in time proportional to their length. And here's the kind of definition that's used in this paper for a reverse, where we kind of take an intermediate step where we kind of write this function go that converts a list into what's called a difference list, or a function from lists to lists, which will take all of these elements in the first list and then kind of reverse them somehow, or build up a function which kind of will all kind of add these on in the reversed order. So if there's no elements to add on, we have the identity function. If we have a non-empty list as input, we build up a function where the first thing we do is kind of push the head of the list on a stack, and then we kind of continue pushing the other elements on the stack. And then once we've built up this function, we can apply it to the empty list, and then we have the reverse list that we were looking for. And if we kind of expand a little bit, you can recognize back that you see this is the typical definition of reverse using an accumulating parameter. And what's nice here is that it now kind of works in linear time. And if you're interested in a definition of list reversal that also works in constant space, you should check out Anton's talk tomorrow. Oh, it sort of messed up the formatting on this slide. Sorry about that. So what happens if we try to reverse a vector in the same style, right? We can take the definition with an accumulator and try to write that out for our vectors. And unfortunately, here, things don't go quite so smoothly. And what's the problem? So we're promising to produce a vector of length successor of k plus m, just as we saw previously for append, I guess. But the problem is that when we make a recursive call with an accumulator, we are making a call on the tail x's, which has length k, and we're extending the accumulator to build a new vector of length successor of m. And these two numbers aren't definitionally equal, so Agda kind of rejects this definition and says that it's type incorrect. So what's really going on here is that we have a mismatch all of a sudden. The definition of reverse is tail recursive using an accumulating parameter, and addition is just defined inductively on the first argument. So the question now becomes, can we find a better definition of addition that lines up with this reversal function and choose a different type for our accumulating reverse so that we don't have to run into these problems with types? And we can. So what we do here is we define an accumulating version of addition, which is tail recursive, kind of behaves the way you would expect, and it kind of mimics very closely the definition of reverse that you want to write. And now this goes through smoothly, and the crucial change here is that I've moved from the type of reverse act being returning something of type n plus m to actually having the same structure in both my type or the functions used in my type and the function that I'm defining, in this case, this accumulating reverse function. So far so good. I mean, we're winning. It seems like we're doing okay. There's just one thing I still have to do is I need to kind of make a call to reverse and kick that off with the empty vector. No, this doesn't work. So why is that? Well, if I look, I'm promising that reverse is a function that preserves lengths. And now if I call my accumulating reverse function with the list x's and an empty accumulator, that has a type which is no longer definitionally equal to n. So remember, the definition of my accumulating reverse was by induction on the first argument. So this computation, add act n0, gets stuck. I can't do any other work, and Agda rightfully rejects this program. So what can I do? Well, one thing I can do is I can kind of show Agda who's the boss, and I can give a proof, right? And give an inductive argument showing that 0 is really the right unit of my accumulating addition. And I can use that proof and to write a coerced vec function, which says, well, if I can show that the length of two vectors are equal, I can map one vector to the other, and then I can complete the definition of reverse and kick it off with an initially empty accumulator. This is fine, right? I mean, this works. Agda accepts this definition. But I think one of the points that I've tried to make so far is that how you structure your definitions really matters. And in particular, if there's anything else, like another proof, or maybe I use this reverse function somewhere else when I want to prove things about that function, having these kind of proof arguments, like showing that 0 is the right unit of my accumulating addition, it can complicate everything that comes after this. So it'd be nice if there was actually a definition of my reverse, which was both linear and didn't use any of these proof arguments. So let's try to find that. And the good news is there's actually a hint that we can take in this paper by John Hughes again. And the key observation that we can make is this construction of using first-class functions to represent lists. It doesn't just work for lists. It works for any monoid. So in particular, what I'll do is I'll come up with a new representation of natural numbers to work with, which I'll call difference naturals. I'm not very good at naming, I guess. And use that to see whether that can kind of push this development a little bit further. So what are difference naturals? Well, just as difference lists are functions from lists to lists, different naturals are functions from naturals to naturals. They can define a pair of functions, one which converts a number into a difference natural by partially applying addition, and a way back which takes a difference natural and converts it back into a number, simply by applying my function to 0. So far, so good. So I mentioned that these difference naturals are monoidal. So what do I have to do to kind of show that? Is I have to define a 0 and an addition operation. So the 0 is just the identity. Remember, these are functions that we're working with. And addition is just function composition. But to really show that this is a monoid, I have to do a little bit more work. I actually have to prove 3 laws, right? I have to show that, I have the right and left unit and that addition is associative. And here's the surprising thing, right? All 3 of these properties now hold by definition. So I don't have to do any induction, I don't have to do any work, and Agda will just accept these definitions once I write REFL. So why is that? So let's look at one example, and all the others are kind of the same. So here's where I show that a 0 is the left unit of addition. So starting from reifying some difference natural dn, reifying is simply applying to 0. Working in the other direction, I now have the addition of 0 and some difference natural, which is function composition. But d0 is just the identity function, and then reifying is applying to 0, and then the identity function doesn't change anything. So my left and right hand side are really equal, and the only thing I've done here is unfold definitions. So this seems like a really useful trick. Now the next question is, can we use this in our definition of vector reverse? So let's try it, right? Let's revisit our accumulating vector reverse. But now, instead of kind of indexing by 2 numbers, we'll do this funny trick where we'll take a vector which has some length n, and the second accumulating vector which has, well, its length is kind of funny. We're assuming that its length now is actually one of these difference naturals. And then we produce a vector which we get by adding all the n's onto the difference natural. So there are 2 cases. In the first case, we have an accumulator, and we return that. And in the second case, we have a non-empty list and an accumulator, and we want to make a recursive call. So the recursive call we make is on the tail x's, but now we need to extend our accumulator, and we hit a problem. What's the problem here? So what we'd like to do is extend the accumulator with a new successor. That would be building a successor and then extending the accumulator in this fashion. But the problem is that what we're promising is that we actually extend the accumulator in a different way. That by kind of growing the by growing the n here, that these 2 things are equal. And once again, because we don't know anything about the difference natural, there's no guarantee that it will actually commute with the successor in this way. So it seems like we're kind of stuck. But suppose we actually had a function which had the type that we're looking for, right? Or we had a decons operation, which for any n and for any difference natural, we have an element, we have some accumulated vector that we've built so far that we can add things in the way that we want to this vector. So cons doesn't have this type, unfortunately. Well, unless I know that when I start off the computation, I'll instantiate the difference natural to 0 to start with. So dm will be the identity function. If I plug in the identity function for dm, I can see that cons has the right type. And curiously, as I kind of go down the one list and go up, kind of accumulating through the other list, it turns out that because this happens in lockstep, I increment dm and decrement n in every step. It turns out that cons can actually still be used in the right way, provided I kind of pass it in as an argument to my accumulating reverse. So what does that look like? Well, it's starting to get a little bit more complicated now. Let's look at this line, the third line of the definition first. So there we can see that's the familiar accumulating type for accumulating reverse. In the top line, it's more gnarly, where we have a difference natural dm, and then we have this huge expression, which is basically the type of the decons operation I had on the previous slide, the thing that I really needed to complete the definition. And then I can see that I can complete the definition this way, and I can kick off the definition the way I'd like by passing the identity function d0, cons, which I'll use to add to the accumulator, my list x's, and an empty accumulator nil. And then everything type checks. Act is happy. Hooray, we've won, but at what cost? So there's another definition of vector reverse that many functional programmers are familiar with, which is using a fold L. So the idea here is that I can reverse a list using an accumulator by consing every new element that I see onto this list. But kind of trying to use this for vectors, unfortunately, doesn't work very well. So why not? Well, suppose I try to define this function, a length-preserving linear reverse on vectors, I get stuck very quickly. So crucially, remember that the argument that I pass to the fold L has to have type A to B to B. But now I'm passing in a function cons, which goes from, or flip cons, which goes from A to vector AN to vector which is one longer. So the B types are no longer identical, so the program doesn't type check. What can I do? Well, it turns out I can be a little bit more general and define a version of fold left which doesn't just return a single B, but actually returns an n index B or net index B. What does that look like? Well, I can see that I take a vector of length n and I produce not just a B, but a B at index n. In order to do this, I need to provide my initial accumulator B0 and a function which I can kind of take a bk in the head of the list and turn it into a B of successor of k. So the first line is not unsurprising, right? If the list is empty, I know that n is 0, I have to return a B0, and I happen to have the accumulator, which is a B0, right kind of in front of me, so I'm done straight away. But the second case is really not so obvious. So what you can see here is that I'm going into making a recursive call on fold L on the tail x's. Oh dear. Sorry. Patrick was just pinging me in Discord. Excuse me. So what you can see here in the recursive case is that x's is actually now has length k, but we're promising to produce something of length successor k. So how could that possibly work? Well, the trick is that we're doing the same thing. We're doing this pre-composition with successor in order for the recursion to go through. But then we have to pass not just a B0 as the accumulator, but a B1, which we get by applying our step function. And now we can define reverse without any proofs and get a linear time reverse function, which is familiar to everyone in the room. But wait, there's more. There's nothing kind of special about natural numbers. This kind of Cayley representation of monoids as endofunctors works for any monoid. And kind of it's a well-known kind of representation of groups, and it's not quite as novel as the title of John Hughes's paper suggests. So in the paper, there's an example of indexing a decision tree by a list of variables in scope. But what's really nice is because the monoidal equalities all hold definitionally, we can exploit that information to write a little monoid solver. So doctors hate him because this Arthur Cayley can solve any equation over monoids with this one weird trick. And let me explain that trick. So I'm going to sketch this very kind of in broad strokes, but suppose I have a set A, which is the carrier of a monoid. I'm going to fix that set in the rest of this talk. And suppose I can write a little deep embedding of this monoidal expressions, right, which have either constants, they have 0 and plus. Then I can write a little evaluator which maps these expressions into A values easily enough, where I replace 0 by the 0 of the monoid, addition by the addition of the monoid, and for all the variables and constants I encounter, I just return the A that I have in front of me. So now I can do the Cayley representation trick, taking an expression, turning it into a function, taking a function, turning it into an expression. We've seen that a few times this talk already. And crucially, I can now normalize any expression. Basically, if I have an expression which is built up with lots of zeros and units, zeros and additions, this will actually turn it into a list of all the things that I'm adding, essentially. I have to do one proof, and that proof says, well, for every expression, if you normalize it and then evaluate it, you'll get the same result as just evaluating that expression. This is a few lines long, and it's not that very interesting. But why I mention it is I can use this to now kind of write my monoid solver, where I pass in two arguments, and these two arguments are expressions, and I believe these two expressions to be equal. So they're built up from the monoid operations. And then I need a kind of proof, which is hopefully just going to be very easy. It's hopefully just going to hold by calculation, namely that normalizing the left-hand side and normalizing the right-hand side of my expression are equal. And if I have that, then I can get that my two expressions are equal. So to call our solver, all I need to do is kind of quote the two sides of the equality that I'm trying to prove. So what I can see here is I'm trying to prove an equality over a list, so I have to write an expression E1, which represents the left-hand side, an expression E2, which represents the right-hand side, and now I can call my solver, and all I need to do is pass in REFL, and I'm done. So this construction works for any monoid, in particular the monoid of natural numbers using accumulating addition. So to come full circle, I don't really have to do the proof. I can now use this monoid solver to complete the first definition of reverse that we saw. So to recap, the Cayley representation of a monoid satisfies the monoid laws by definition. And that's a useful trick to have whenever you're programming with dependent types. So this might be particularly useful if you're writing functions with an accumulator, and this accumulator is indexed by a monoid. And whether this is very useful or not kind of depends on your tolerance for complicated type signatures. And crucially, you can use the same trick to solve monoidal equations for almost free, kind of with a little bit of work. You need one very short proof. That's all I have time for, but thanks very much. I'm happy to take questions.
Yeah, same procedures before. Micro. Okay, no microphone questions so far. I've got one question. So usually
Sure.
when you finally get something to work out fine in Agda, there are still some gnarly cases. So when does this not work?
So it's still it's not trivial to reason about these things, right? So even if you have a definition using full del, which is very short and sweet, and it kind of fits in 3 lines, that's great. But then if you want to do any proofs, you have to be very careful and generalize in the right direction so that you can actually still use your induction hypothesis. There are a few other examples in the paper, I think, that might be interesting.
Any other questions? Okay, then we'll just thank the speakers and take the break.
Thank you very much. Thanks for having me. Enjoy the rest of ICFP.